First things first, you'll notice on your Moodle site that I have turned off a few things, and then we have our Chapter 3 notes. Because Chapter 3 is kind of a big chapter. This is the chapter on derivative calculus, so we're going to be looking at that and as its entirety, and then getting into other aspects of this concept of derivatives with chapters 4 and 5 and so forth and so on as we're going through this stuff. So, we had a test on chapters 1 and 2, and then I had a test. And then at the end of chapter 3, we're going to have another test. And my goal here is throughout the semester is to have 4 tests, okay? So be prepared for that. So I hope you've already got these notes on, and we'll be adding to these notes as we start to look at this stuff. And so also you'll notice that right now there's no web work up for you guys, but don't worry, by the end of the day, we'll start the web work process all over again. I'm just going to set the dates and stuff. So, all right. Before I get started on chapter 3.1, where calculus really begins, is the concept of limits. Got a question for you guys. How'd you do on my test? You felt real good about failing. Okay, I got that. All right, great. What did the test look like? It was the homework. I just took the template and just changed the numbers. Huh? Wow. Add them together and divide by 2. You're right. I didn't put that on there. But I also told you guys while my review that don't forget to review midpoint formulas, distance formulas, and obviously all the other things that we did, because when I made up the homework set, I tried to mimic how many questions and the type of questions that I was going to do on the test. And obviously because the homework was a little bit longer, I actually shortened it up a little bit just to make it much doable. I had folks in here turn that test in within less than 45 minutes. You had 75 to do it. But most folks turned it in and honestly, a little bit more than an hour or so, which is a good length for a test. Of course, some people had to yank it out of their hands and then some. It's just normal for tests and stuff. But my question to you is this. How did you do? Now, I've got preliminary results back on the multiple choice part and stuff like that. So you guys did okay on that. But the big point totals are with that free response part. And it usually takes, for the number of students I have in here, usually takes about a week for me to get the test turned around and put it all back together again. So my goal is to turn back the test on Wednesday. So that's what I'm trying to get. So always prepared for that. And it depends on if my grader can get it back to me in time, because we are looking for, if you did mess up on some of those ellipses, hyperbolas, and the questions I was asking, the way I set it up, you notice I changed it slightly from the homework to the test, but that was to make it easier for us to grade and stuff like that. So I've got particular questions. Whether you graphed it or not, that's up to you. Didn't have to, but it helped to figure out where things are located on the major axis or whatever the case may be. But I did, so I am looking for partial credit on certain things. So if you think you screwed up one big one, because here's the thing, and this is going to surprise and hurt a lot of people, there weren't that many questions on the multiple choice. I mean, you're expecting all those line questions, absolutely. But then I had, 2 major problems, because it takes so much time to do, an ellipse and hyperbola and that type of problem stuff. I think obviously I had some circle stuff up there too, but there weren't that many questions. And what I typically do is on every section, I make it out of 100% or 100 points or whatever, and then I will do some type of averaging between the 2 sections to get the total for your grade. And so the point totals on the free response added up to 100 points, which does make each problem work between around 15 to 20 points apiece. So when you screw up one, you're killing, you shot your A, you shot your B, you're in the C rank. Well, but you also got to remember this. That's out of 100 on that section. With the other section being also out of 100, basically take those numbers and divide by 2 is the real point total. So if it is a 20-point problem, it does mean legitimately on the test, it's going to be worth at least 10 points for you guys. So yeah, I will be grading off partial credit in case you screwed up some kind of a number or something like that, the problem is with this stuff, like all math, if you screw up one part, it has that residual effect of making you screw up the next part and the next part and the next part, and the next thing you know, you missed a whole problem because you messed up that one little part right in the beginning. So I am looking at grading on partial credit to see what you did and where your mistakes are at. But even then, you know, it really depends on what you did to actually show the net result and things. So my goal here is, honestly, it takes me about a week. So next class period, I should have your test back for you guys. So we'll take some time and pass back the test and stuff. And I usually like to do that at the end of class because I want your undivided attention on this. Section 3.1, the concept of limits. First off, let's go through the definition. So let me blow this thing up here. Definition. The limit as x approaches a, and this is how you read it, lim for limit. Limit as x approaches a of f of x equals L. And I wrote it out for you. The limit as x approaches a equals L, where f is the function valued headed as x is on its way to a. Now, I'm trying to do this basically concept from an English perspective, but here's the real deal. Let me explain limits to you guys. All right? In a nutshell, you've got a problem point, and that problem point is at A on a particular function, okay? So you've got a problem point at A. What do I mean by a problem point? Let me give you an example. You're working on a circuit. And I know every time that I throw in 3 amps on this circuit, the thing melts. Complete blow up. Fire, people die, it's awful. When I throw in 3 amps on this thing, the thing just completely melts. I've got a problem someplace. 2 amps seems to work, you know, so forth and so on. This is the concept of a limit. So, 1, I know I got a problem at 3 amps. So I rebuilt my circuit the exact same way as I did the other one. And what I do here is to figure out what's going on at 3 amps. So I'm going to turn on the circuit. I'm going to throw in 2 amps. The circuit's working fine. Then I throw in 2.5 amps. Circuit's working fine. But I know at 3 amps that sucker's going to blow up. So what am I going to do? I'm going to throw in 2.7, 2.8, 2.9. Now the circuit's beginning to shake a little bit on the table and stuff like that. Still having a good voltage output, but it's beginning to do it. 2.91, 2.92, 2.93, 2.94, 2.95, and I'm monitoring exactly what's going on with the circuit until 3, boom, blows up. This concept of an incremental approach is by definition what a limit is, okay? So, now I'm doing all this fancy stuff, doing the mathematics behind it. We take the limit as x approaches a. Now, our circuit or whatever we're playing with, that's my function. A is my problem point, okay? And I'm trying to figure out what's going on at A. So, right there at A, I could tell you, when I threw in, 2.5 amps, I was getting 4.7 volts. I threw in 2.95 amps, I was getting 4.95 volts. As I threw in 2.99 amps, I was getting 4.98 volts, okay? So it looks like when I throw in 3 amps, when it blew up, what was my voltage coming out of that thing? About 5 volts. That would have been the limit value, that 5 volts. What is this thing going towards before it blows up, okay? Now, this concept of blowing up is an exaggeration, but not really. And this is the real world application of this stuff. But from a mathematics perspective, we're going to sit there and take the limit as x approaches a. A is my problem point. I'm trying to figure out what the function is going towards. Okay? Now, there's 2 ways we can handle limits. You can approach it from below, or you can approach it from above. You see this first one. Take a look at the notation. You would read this. Take the limit as x approaches a. You see the little minus sign? But the minus sign is not in front of the a, it's behind the a. So this will be taking the limit as x approaches a from below a. That's exactly what I was doing when I was taking the limit as x approaches 3 on my circuit example. I was actually taking the limit as x approaches 3 from below. We went 2.5, 2.7, 2.9, 2.95. We're getting close to 3 from below, okay, of my function. Now, but I could have also done this, went the other direction. I could have taken my circuit and thrown in 4 amps, and let's see what happens there. And then I throw in 3.5 amps. Then I throw in 3.1 amps. Then I throw in 3.05 amps. Then 3.01 amps. You know, I'm getting closer to 3, but I'm approaching it from above. How you do it from above is you take the limit as x approaches through a from the little plus sign up behind it. That means from above. So number is slightly bigger than a. And you're seeing what's going on. This will be called the limit as x approaches a from the right. So in a nutshell, when you're taking limits, understand limits like this. Okay? So I do my Star Trek example here. You've got this hole in space, right? And if I jump right on that hole, you get sucked off to some other weird parallel universe or whatever. You've seen Star Trek, you know. Okay, so right there is where my hole is located at. But I'm trying to figure out what's going on at this particular hole. So what am I going to do? I'm going to try to get very, very close to the hole without actually being right at the hole and try to peer over and see what's going on at the hole. So I'm actually trying to get, so here's the idea behind limits. Okay? So you've got this hole in your space. It's off the page there. All right. So you got this hole in space. Let me reduce it down. So here's some kind of function right here, and that hole is located at A. Okay? I'm trying to figure out what's going on here. Okay? So, as I approach A from below, we're going to plug in numbers very, very close to A, but slightly less than A. This would be the limit as x approaches A from below, from the little minus sign there. And you plug it into the function, and you're trying to get as very close to the hole as possible to see what's happening at the hole. I mean, by seeing what's happening at the hole, you're looking for what we call the limit value. So in English, the limit value is the y-coordinate of where the hole is located at. But you see, there is no y-coordinate of this because there's a hole there. There's no dot. So it's what the y-coordinate would have been, the location of the hole y-coordinate. That's the limit. And you take the limit as x approaches A from above or from the right. This will be that limit as x approaches A from the plus side. From the plus side, you plug numbers in slightly bigger than A, and you plug them in, you try to figure out where that limit value is. And when the limit from the left is equal to the limit from the right, you're approaching the same number, that's your limit value, L. Now this is, in a nutshell, exactly what you're doing with limits. Okay? And I wrote it down here. For a limit to exist in general, the limit from the left must equal the limit from the right. That is, the limit as x approaches A equals L, if and only if, when I take my limit as x approaches A from below, of f of x, it equals L, and that's also equal to the limit as x approaches A from the right. So here's the deal. If the limit from the left does not equal the limit from the right, then we say the limit does not exist. Okay? But now, we're going to do this from, one, a functional perspective, and the other one from a functional perspective. So, let me show you the easiest method. So I'm basically cliff noting this stuff for you guys from the text, from your textbook and how it's written up in your textbook and stuff. But this is what's really going on here. This is a limit. I want you to take limit as x approaches 3 of x squared. Here's the deal. Look at the function x squared. You know that one. What does a graph look like? What does x squared look like when you graphed it? It's a parabola. Is there any problem with x squared? No, I pretty much know how that graph works. Is there any problem, especially at 3? No. What I mean by a problem is this. What is the domain of x squared? What kind of numbers can you plug in x squared? All real numbers. You can plug in negative numbers in squared. You can plug in 0 in squared. You can plug in positive numbers in squared. There's no problem with x squared. So the first rule of limits when you're doing it from a calculus perspective is plug in a number. If there's a problem, don't worry, you'll recognize a problem when you actually violate some rule of mathematics. But in this problem, x squared's pretty nice. Take the limit as x approaches 3, so the first rule of limits is plug in a number. So 3 squared. If you get a number, you're done. What's the answer? 9. The limit as x approaches 3 of x squared is 9. Now, if you want a visual for this, sure. This is what's going on. here is the graph of y equals x squared. Here's my point 3. When you graph 3, you get 9. 3 squared is 9. But to understand what's really going on here, as I take the limit as x approaches 3, it means I go from below 3 and above 3. What number is the y coordinate approaching on either side? What number is it going towards? 9. The problem is, what makes it easy is the fact that x squared, quote, doesn't have a problem. Okay? Let's define when we have a problem. You can't divide by what number? That's a problem. You can't take the square root of what kind of numbers, or even roots of what kind of numbers. That's a problem. When you violate some kind of weird domain rule, that's a problem. But this one, x squared, that domain's all real numbers. That's not going to be a problem. And if that's the case, first rule of limits is plug it in. Take a look at this problem right here. The limit as x approaches 1 of 1 over x. Look at the function 1 over x. Does it have a problem? Actually, it does. 1 over x has a problem. What value of x would cause this thing to have a problem? 0. 0 is the problem point. But that's not the point we're after the limit for. What limit are we going after? 1. So at 1, this function 1 over x doesn't have a problem. So the first rule of limits is plug in a number. If you get a number, that'll be your limit value because, quote unquote, you didn't have a problem with that function. You know, if I got a circuit and I plug in 3 amps and I get 5 volts out of it, that's awesome. 5 volts is what my limit value is going to be when I get close to 3 amps. There was no problem with my circuit. But when my circuit starts to melt and blow up and stuff when I throw in 3 amps, then I got a problem. Then you're going to have to do this incremental approach. Does that make sense? So for this problem, what's the limit as x approaches 1 of 1 over x? Well, first rule, plug it in, 1 over 1, which is equal to 1. So my limit value is 1. First rule of limits, and we call it plug it in. First rule of limits is plug it in. Then, let's take a look at the next stuff. Next set of examples here. Okay? Take the limit as x approaches 4 of 4, take the limit as x approaches 4 of x minus 4 over x squared minus 16. What's the first rule of limits? Plug it in. Let's see if we're going to have a problem or not. So first rule of limits is plug it in. When I plug it in, I'm going to get 4 minus 4 over 4 squared minus 16. All right? 4 minus 4 over, what is 4 squared? 16 minus 16. What's 4 minus 4? 0, and 16 minus 16? 0. I get 0 divided by 0. That's a problem. But here's the deal. Let's go back to your original algebra pre-calculus skills here. A number divided by 0 doesn't exist, right? So officially this answer, quote, does not exist. But this is something special. It's not just a number, like 5 divided by 0. This one's special. This one is 0 divided by 0. Let's look at other numbers. If I happen to have 5 divided by 5, what's 5 divided by 5? 1. What's negative 7 divided by negative 7? 1. What's, no, negative 7 divided by negative 7 is positive 1. Okay. Okay. What is 3 divided by 3? What is 0.5 divided by 0.5? What's negative 0.1 divided by negative 0.1? Well, so basically when the same number is on top, on bottom, they should cancel, right? So why isn't this answer 1? Well, sometimes it is. But sometimes when the zero is on top, 0 times anybody is 0, so sometimes the answer is 0. And when you divide by 0, that doesn't exist, so sometimes the answer is does not exist. This is what we call indeterminate form. Zero divided by 0. Because the indeterminate form, you can't tell what's going on here. Because sometimes it's going to cancel, sometimes it's not, and you get 0, or sometimes you can get does not exist. So this is where your, quote, problem case is going to be at. Now, here's the deal. When you do get 0 divided by 0, all right, let's go through my steps. Step number 1, first rule of limits is to plug it in. Plug in the number. If you get a number, you're done. Second rule of limits is this. If you get 0 divided by 0, then I'm going to quote, do algebra. Do algebra. The goal is the hope that 0 divided by 0 cancels. You know, all the other numbers cancel, so maybe it does cancel. The only way you're going to figure that out is, quote, do algebra. So go back to your original problem. Take the limit as x approaches 4 of x minus 4 over x squared minus 16. What kind of algebra would you do on this thing? Quote, unquote, I want to clean this thing up. How would you clean this guy up? What would you do to clean this guy up? I would factor which one? A denominator. X squared minus 16. How does that factor? All right, so what is it? Take the limit as x approaches 4 of x minus 4 over x minus 4 times x plus 4. Do you see anything canceling? Yes. Yes, you do. Remember, you can only cancel through strict multiplication division. Okay? Strict multiplication division, only time you can cancel. But once I factor things, I turn things into multiplication, and what cancels here? X minus 4 is canceled. You're left with the limit as x approaches 4 of 1 over x plus 4. So, quote unquote, you have cleaned up the problem. Okay? And after you clean up the 0 divided by 0, then what are you going to do? Go back to step number 1. Plug it in. When I plug in, limit as x approaches 4. When I plug in x is 4, what do I get? 1 over 4 plus 4, which is equal to 1 over 8. And when you get a number, that's your answer. That's your limit value, 1/8. Does that make sense? Have I lost you guys anywhere? All right, let me be very clear and concise with you. This is calculus class. And in calculus, we're not just interested in the answer. We're interested in how you got the answer. Okay? So the answer is just half the problem. It's how you got the answer. And of course, no work means no credit. So if you just got the answer with no actual work involved, you get absolutely no credit. I think I'll take off extra points making me look at crap without any work done. Welcome to being a math professor. But now, here's the thing. Look at how I wrote up the solution. So I'm not just interested in how you got, 1/8 is the answer. That's awesome. How did I write up this answer? First things first. Here's my original question. Limit as x approaches 4 of x minus 4 over x squared minus 16. First thing I did was plug it in. See what's going on. Okay? And you'll notice that once I plug in a number, I don't write limit anymore. I'm just plugging in a number and just crunching it out. But now, once I had 0 over 0, I went back and wrote up the problem. Limit as x approaches 4 of x minus 4 over x squared minus 16. Then I did algebra on that x minus 4 over x squared minus 16. But I continue to write limit as x approaches 4 in front of each algebra step that I did. And then the x minus 4's canceled. I wrote limit as x approaches 4 of, when you clean it up, you got 1 over x plus 4. But notice something, brother. At the point that I actually plugged in the number, what did I not do anymore? I didn't write limit anymore. Now I just plugged in the number, 1 over 4 plus 4, and crunched out my answer. This is the proper etiquette of mathematics when you're doing limits. When you're manipulating the algebra on a problem, you keep writing limit, 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 limit every time until the point that you actually cancel and plug in the number. Until the point that you actually plug in the number, that's when you stop writing limits. So it's not just about getting the right answer. It's about how you wrote up getting that right answer. Does that make sense? That's traditional calculus. Not just about getting the right answer, but writing how you showed the work and the proper work in getting this answer. Okay? So let's do another one. I'm going to pull over the page before I jump on the next one here. Okay? Take the limit as x approaches -2 of x squared plus 4x plus 4 over 2x squared plus x minus this one. Okay. Take the limit as x approaches -2 of x squared plus 4x plus 4 over 2x squared plus x minus 6. So I'm going to throw in some extra examples of this because this is the most important aspect of limit. It's that 0 over 0 case. That's where you're going to identify problems. Okay. So here we go. Take the limit as x approaches -2 of x squared plus 4x plus 4 over 2x squared plus x minus 6. What's the first rule of limits? What you going to do? Plug it in. Let's see what we get. If I plug it in and get a number, I'm done. So this will be -2 squared plus 4 times -2 plus 4 over 2 times -2 squared plus -2 minus 6. All right, let's see what we get here. -2 squared, well, that's 4. 4 times -2 is -8 plus 4 over -2 squared is positive 4 times 2 is positive 8 minus 2 minus 6. 4 minus 8 plus 4 is 0 divided by 0. 8 minus 2 is 6 minus 6 is 0. It's the famous 0 over 0 case. Don't be surprised when you see a lot of these kind of problems in your future. All right, so what am I supposed to do with this one? All right, so with this one, pay attention to my words. This one is polynomials divided by polynomials. Traditional trick on cleaning this up is to factor your polynomials. With a 0 over 0 case, something should factor. Well, let's see here. So when I write it up, this will be the limit as x approaches -2 of, now this is x squared plus 4x plus 4 over 2x squared plus x minus 6, the original problem, equals the limit as x approaches -2 of, how would you factor that numerator? X squared plus 4x plus 4. X plus 2 squared, or x plus 2 times x plus 2, right? Most folks can handle that one. You know, here's the one that kills people. What about this 2x squared plus x minus 6? How's that one going to factor? Well, because you got a 2x squared, nothing's in common here. If you had something in common, factor it out of everything. You're going to have to factor it as 2x times x. And what times what is 6? That one, I remember the trick is when you pull it back out, I got to get a plus x in the middle. I'm thinking of 2 and 3. And I want to multiply this 2 times this 2. That'll give me 4. And that'll be 3 there. And 4 minus 3 is going to be 6. That's a minus at opposite signs. And I want the one with the bigger number to be plus. So I think this is going to be plus. This will be minus. You understand this anti-folding stuff. No doubt you've done it hundreds of times before, but if you screw up the factoring, you're dead in the water. How do I know I got this one right? That I factored it correctly is what I mean. Pull it back out. 2x times x is 2x squared. 2x times 2 is 4x. Minus 3 times x is minus 3x. 4x minus 3x is x. That matches up. And then last, -3 times positive 2 is the minus 6. Does that make sense? Now, what cancels? X plus 2's cancel. So this would be equal to limit as x approaches -2 of x plus 2 over 2x minus 3. So, and again, it's not just about getting the answer. Notice the work and how I wrote it up to get this thing. Now what you're going to do? Plug it in. This will be -2 plus 2 over 2 times -2 minus 3. -2 plus 2 is 0 divided by 2 times -2 is -4 minus 3 is -7. What is 0 divided by -7? 0 on top is 0. 0 on bottom is undefined. 0 divided by 0 means do algebra. Does that make sense? So where's this one at? 0 on top. My limit is actually 0. Does that make sense? All right. I'm giving you one example of every different type I can throw at you. This one is polynomial over polynomial. Try this one. Take the limit as x approaches, let's pick us a number. -3, okay, of 2x plus 6 divided by the square root of x plus 7 minus 2. All right. Something new has been added. Okay, so here we go. Take the limit as x approaches -3 of 2x plus 6 divided by the square root of x plus 7 minus 2. First rule of limits, what you going to do? Plug it in. When I plug it in, I don't write limit anymore. We just plug in the value. 2 times -3 plus 6 divided by the square root of -3 plus 7 minus 2. Well, let's see here. 2 times -3 is -6 plus 6 divided by the square root of -3 plus 7. What is that? Square root of 4 minus 2. That's -6 plus 6 is 0 divided by, what's the square root of 4? 2 minus 2 is, what a surprise, 0 divided by 0. Does that make sense? Did I lose you guys anywhere? So, here's the deal. When you get 0 over 0, what are you supposed to do? Do algebra. That's the code for the 0 over 0. Do algebra if you can. Okay? If you can. All right, so what kind of algebra will you do on this one? Well, when it was a polynomial divided by polynomial and you got 0 over 0, the trick was factoring. When you got a radical with this stuff, the trick is, no, there's no saying equals 0. This is not an equation that you're trying to solve for. This is basically manipulate the, simplify the expression. But the trick is this guy. Have you ever heard this word before? The trick is conjugates when you've got radicals. What is the conjugate of the square root of x plus 7 minus 2? Square root of x plus 7 plus 2. You change the sign of the middle guy. Have you guys heard of this conjugate stuff before? We did it when we had complex numbers back in our college algebra days. The conjugate of like 3 plus 2i was 3 minus 2i. Okay? But when you're dealing with i's, you really are dealing with square roots. Square root's a -1 type thing here. So when it comes to the conjugates of radicals, the square root of something plus or a number, this conjugate would be the square root minus a number. You just change the sign of the middle guy. So this problem now is going to turn into the limit as x approaches -3 of 2x plus 6 over the square root of x plus 7 minus 2. And what I'm going to do here is I'm going to multiply by the conjugate of where the radical is. What is the conjugate of the square root of x plus 7 minus 2? Square root of x plus 7 plus 2. But this is not an equation. So we've got to do this algebra thing of simplifying. Whatever I do to the denominator, I also have to do to the numerator, which means I'm actually multiplying by a ratio of 1, which officially does not change my problem. So I'm multiplying by the square root of x plus 7 plus 2 on the bottom, and I'm going to multiply by the square root of x plus 7 plus 2 on top. The conjugate of the original problems, in this case, the radical. Does that make sense? When you do this, again, I'm doing the algebra and showing you every different kind of algebra problem I can throw at you guys. Change numbers, but you'll have to do the same thing. When you've got a radical in it, you need to do conjugates. So, here's the deal. Listen to my words and get it in your notes. When you're doing one of these conjugate problems, you always want to FOIL out conjugates and leave non-conjugate multiplication in factored form. Because remember, the ultimate goal with 0 divided by 0 is to cancel something. Okay? So, when it comes to the conjugate paired stuff, you want to FOIL that stuff out. So this will be equal to the limit as x approaches negative 3 of 2x plus 6 times the square root of x plus 7 plus 2. Non-conjugate paired stuff, I just leave in factored form. It's the denominator that I'm going to multiply out. Help me out here in pulling this out. What is the square root of x plus 7 times the square root of x plus 7? X plus 7. Squares and square roots cancel each other out. Square root of x plus 7 times square root of x plus, the square root of x plus 7 times the square root of x plus 7 is the square root of x plus 7 squared. But this square and the square root cancel. You with me? Then we've got to do outer. Square root of x plus 7 times 2 would be plus 2 square root of x plus 7. Inner, negative 2 times the square root of x plus 7 would be minus 2 times the square root of x plus 7. And then last, what is negative 2 times the positive 2? Negative 4. Here's the trick when you deal with conjugate pairs. When you FOIL them out, the outer inner always cancels. The outer inner always cancels. So what cancels here? 2x, 2 times the square root of x plus 7 and minus 2 times the square root of x plus 7. That was the outer inner on the FOIL method, canceled. Combine like terms. This is equal to the limit as x approaches negative 3 of 2x plus 6 times the square root of x plus 7 plus 2 divided by x. What is 7 minus 4? Plus what? 3. 7 minus 4 is 3. The ultimate goal of 0 divided by 0 is to cancel something out. Does that make sense? So, what cancels? Well, I don't see anything canceling yet. But wait, I see this term right here. You see it? 2x plus 6. What you can factor out a 2. You got a 2 in common on this thing, right? So on this little part, you again keep the non-conjugate paired stuff in factored form. But if you got other stuff you can factor out, you yank it out. So this would be, again, notice I'm writing the word limit every time until the point that I actually plug in the number. The limit as x approaches negative 3 of 2 times x plus 3 times the square root of x plus 7 plus 2 divided by x plus 3. What cancels now? X plus 3's. So this would be equal to the limit as x approaches negative 3 of what's left? 2 times the square root of x plus 7 plus 2. Right? Now, once you cancel, catch the pattern on this stuff. But once you cancel, then the goal is to plug in the number. And once I plug in the number, I don't write limit anymore. That lets me know, the mathematician know, that you're actually evaluating this thing now. So this will be 2 times the square root of negative 3 plus 7 plus 2. This will be 2 times the square root of negative 3 plus 7 is 4 plus 2. All right, let's tell me what you get here. What's the square root of 4? Plus 2 times 2. My answer is 8. The limit value is 8. Notice how I did the problem. I am kind of quote-unquote turning the heat up on you guys, but I'm really trying to show you all the different kind of problems I can throw at you guys. Does that make sense? Did I lose you guys anywhere? Yes?
When you say square root of 4, when you say plus 2, that's 4 times 4.
Yeah.
I couldn't see that.
The arithmetic I can handle. Okay, so you're welcome. All right, so does this make sense? I lose you anywhere? Well, what's another one I can give you guys that would make you squirm in terms of quote through algebra? All right, we'll try this one. Take the limit as x approaches 2 of 4x squared minus x plus 1 over x squared plus x plus 1. Try this one. What'd you get? What's first rule of limits? Don't ever forget this. You're going to do about 10,000 of these problems. Welcome to your future. On limits and stuff. And it comes to a common place where people want to sit there and they see polynomial, polynomial. They're going to start trying to factoring this guy and try to factor this guy and stuff like that. And they forgot their basic rules. So I did this problem to you guys just to remind you of your basic rules. Don't just start with the algebra and try to cancel some stuff out and assume it's 0 over 0. Because you will screw these kind of problems up if you started manipulating the algebra, trying to do conjugates on problems without checking it first, making sure it's a 0 over 0 problem. So here we go. First rule is plug it in. This will be 4 times 2 squared minus 2 plus 1 over 2 squared plus 2 plus 1. 2 squared is 4 times 4 is 16. 16 minus 2 is 14 plus 1 is 15. Divided by 2 squared is 4 plus 2 is 6. Plus 1 is 7. The answer is 15/7. It was a trick question. But you see, people get so involved in all this weird algebra you have to do, they're going to start doing algebra on this thing and screw it up for sure. Don't forget. First rule, plug in the number first. If you get a number, you're done. But if you get 0 divided by 0, that's when you do algebra, if you can. So here we go. Try this one. The limit as x approaches 5 of 5 over 15 over x 15 times x minus 75 over, let's see here, trying to make one of them. Yeah, 75. So it's 15x minus 75 over I'm making this one. I will do another one of these. X minus square root of x plus 20. We'll do that. One of these problems. What's the first thing you're going to do? Plug it in. This would be 15 times 5 minus 75 divided by 5 minus the square root of 5 plus 20. 15 times 5 is 75 minus 75 divided by 5 minus the square root of 25. 75 minus 75 is 0. Square root of 25 is 5. 5 minus 5 is 0. But you better check that first. Because I could have made this denominator like 3, and 0 divided by 3, the answer would have been 0. So check it out first. But now it's a 0 divided by 0. So this, again, I'm trying to make things look a little more bizarre. What would you do to clean this guy up so you can clean up the algebra? Do algebra. What would you do? Conjugate. So let's rewrite the problem. This is the limit as x approaches 5 of 15x minus 75 divided by x minus the square root of x plus 20. What is the conjugate? Outstanding. X plus the square root of x plus 20. But what you do to the bottom, you got to do the top. X plus the square root of x plus 20. And leave, when you pull this stuff out, you pull out conjugate pair stuff, and you leave in factored form non-conjugate pair stuff. So this equals the limit as x approaches 5 of 15x minus 75 times x plus the square root of x plus 20, right? Divided by, when I pull the conjugate pair stuff out, what am I going to get? I get x squared. I get x times the square root of x plus 20. I get negative x times the square root of x plus 20. And negative times a positive is a negative. And then what do I get here? And be careful on this one, why I did this one, because this is where a lot of people have screwed up. What is negative the square root of x plus 20 times a positive square root of x plus 20? Nope. Eventually. But what is it first? What's a negative times a positive? Negative. What's the square root of x plus 20 and square root of x plus 20? X plus 20, but you got to put parentheses around it when you got two terms, because that negative is going to distribute and make it the minus x, the minus 20. Does that make sense? So be careful of that one. Again, you see a lot of students write minus x plus 20, but then they never distribute the negative and they screw up the problem. Does that make sense? Now, clean this guy up. This is the limit as x approaches 5 of, now in this numerator, I could factor out that 15. If I factor out the 15, that'll leave me with x minus 5 times x plus the square root of x plus 20. But let's clean up that denominator. The outer inner on the full ends up canceling out. And what are you left with? Minus x minus 20. But you'll notice something or other. When do I actually get to plug in the number? Right now? No. You only get to start plugging in the number after something canceled. Have you canceled anything yet? I mean, I'm talking about numerator denominator canceling. Has anything canceled yet? No. So now, I got to do one more thing. I got to clean it up some more. How would you clean this guy up? Factor out the denominator. How does that denominator factor? Limit as x approaches 5 of 15 times x minus 5 times x plus the square root of x plus 20 divided by, let's see here, x squared minus x minus 20 is x times x. 20 that differ by 1 has got to be 4 and 5, and my signs minus got to be opposite signs, minus on the 5 plus on the 4. Pull it back out, just double check. What cancels? X minus 5. Strict multiplication division, things cancel. So this would be equal to the limit as x approaches 5 of 15 times x plus the square root of x plus 20 divided by x plus 4. Once you cancel, now what do you get to do? Now you plug in the number. So this will be 15 times 5 plus the square root of 5 plus 20 divided by 5 plus 4. This will be 15 times, let's see, 5 plus 20, 25. Square root of 25 is, plus another 5 makes it 10, over 5 plus 4 is 9. So this answer is 150 divided by 9, but you want to reduce that, so let's see, what is that going to be? 50 thirds? Always reduce your fractions, proper predicate of math. Does that make sense? Did I lose you guys anywhere? But here's the deal. This is your first real calculus problem. Calculus truly begins with the concept of limits. Okay? So, based upon this, notice how much algebra on a problem that I just made up. Now, you're right. I was thinking through my head and trying to come up with a more advanced kind of problem. But look at how much algebra that you actually, from the beginning of the problem, that you actually had to do before getting to the answer. So when you actually run across these kids that are in college algebra or pre-calculus, kick them in the butt. You tell them, this stuff's important because you can't do the calculus stuff without getting that college algebra stuff down. Question? Why not? Is this hard now? No. Let's explain the difference. Is this hard? No. Is this tedious? Yeah, that's different. WebWorks chock full of problems that are tedious, but are they hard? No. Don't worry. I'll get you some hard problems later. This isn't hard. This is just incredibly tedious. But you're trying to get the process out of it. I'm trying to train you guys and make you guys, I'm preparing you not just for this class, but for the next level up, okay? And I'm going to show you guys in the next class, when I come back your test, I'm going to show you why we went over all this conic section stuff, but I was going to wait until you returned your test paper back before I did that, to try to give you guys an insight to your future and to your next level class and stuff. All right. Let's go back to our notes. I just want to throw some more advanced problems at you guys because, you know, I get complaints all the time. Hey, look, those problems you guys put on the notes that I type up and stuff for you guys, those are easy problems. When I get to the WebWork problems, oh, those are hard. No, they're not. They're just more tedious. Okay, so I decided to throw a tedious one at you guys, and let's just work through it. All right, here we go. This is basically, so far we got 2 cases down. Let's go through our cases and limits. First case of limit. Take limits, x approaches something or other, some function. What's the first thing you're going to do? Plug in a number. If you get a number, you're done. There was no problem with the function. There was no problem point, so you actually got the answer. Second one, plug in a number. If you get what? 0 divided by 0, then what are you going to do? Do algebra. Be able to factor something out, and I tell you, factoring conjugates is another algebra you can do. Common denominator on fractions, maybe another algebra you can do. Do some kind of algebra on it so you can cancel something out, then plug in a number. There's the third case, this case here. Plug in a number, and you're going to get a number divided by 0. That's different from 0 divided by 0. So this is the case of a number divided by 0. And let's see what we're going to be doing here. This is not 0 divided by 0. This is number divided by 0. Now, officially, listen to my words. Officially, a number divided by 0 does not exist. 5 divided by 0, no solution, does not exist. Negative 6 divided by 0 doesn't exist. So my answer is does not exist. But there are 3 possible answers of does not exist. What do you mean there are 3 possible does not exist? There is the does not exist that is infinity. There is the does not exist that's negative infinity. And there is the does not exist that just plain old does not exist. So there's 3 different kinds of does not exist. So here's the deal. If you're a gambler, here's the gambling deal. When you get a number divided by 0, the answer is going to be one of 3 different cases. The answer is either infinity, or negative infinity, or D-N-E. What does D&E stand for? Does not exist. That is a D. Does not exist. Okay, let me tell you a true story. Most of you guys know I graduated from NC State. Okay. And as a graduate student at State, first thing you do is they throw you into a calculus class. After you get so many hours of teaching, they give you a week's worth of training on how to become a teacher. And they say, here's a calculus book, the room for Harrelson 208. There's a class waiting for you. Go teach them calculus. This was my introduction to being a college professor when I was a grad student. You've seen them. A lot of students we use, a lot of classes we do in the math department are run by PhD graduate students and stuff. And that's normal at any major university because you've had that much experience with the mathematics that you know the mathematics. But one thing they don't teach you is how to become a teacher. Let me tell you something, brother. There's a lot more to being a math professor than it is just being a good teacher. That communication skills is huge. And I let you know right now, I had tons of my friends that were outstanding graduate students in terms of doing research and mathematics, and you've seen some of these people around here. They're awesome at doing big research and being able to come up with new ideas and applying them and stuff. But they can't teach themselves out of a wet paper bag. They are so sad at trying to explain it to somebody else. Okay? That's you run across them. Physics department. There are tons of those people. I know. Okay, look, we all had to endure these people through every one of us doing the college. You pray and hope you get the great professor, but you're going to run across some of these professors that all they're into is really big-time research. And they're great in their research, and they come up with new ideas and make all kinds of money with research grant money, which makes the university very happy, but you really don't want to put these people in front of a classroom. But, of course, by law, the university has to, because that's part of your job as being a university professor. All right. I had a student, first time teaching calculus class, and I couldn't figure this thing out. We're teaching calculus, and calculus really begins with limits. And I gave him the classic limit test. And the guy on the entire test, this is a state now, I expect these people would be pretty bright, but I was wrong. On this particular test, the entire answer for every problem that I put on the test was 1. Answer was 1. Gave him a limit problem on this, answer was 1. Gave him a limit problem on this, answer was 1. Every problem on the entire test was 1. And it just killed me going, I don't even understand what this guy is actually doing here. Well, every answer is 1. Come on now, at least the answer sometimes is 1. Sometimes it's 0. Sometimes it was, 8, 1/4, 1/3. We got lots of different answers on this thing. Why is the answer 1 every time? And then as I was looking at the guy's paper, I figured it out. He thought it was an O. O-N-E. So every answer just was O-N-E. Must be 1. So obviously the guy was on drugs or something. I don't know. But obviously he failed my class and failed out of state and went to the community college or something. I don't know. But I have no idea whatever happened to that fella, because he never became an engineer, I assure you. Because I don't really have no idea, but it just completely floored me when I figured out what he was finally doing. I had to laugh about it. Then I had to fail him, you know. But, all right. It's a D, just want to let you guys know about it. And honestly, that's a true story. And I mean, you understand how upset I was, because everybody else's paper, everybody else was making 90s on the test and stuff. I was excited about it. This dude, I think he actually made a 10. You know why? One of the answers was 1, yeah. So I had to give him credit for that one. But, all right, so here's the deal. When you got a number divided by 0, it's 3 cases. Because officially, number divided by 0 does not exist, but there's 3 versions of does not exist. There could be infinity, or negative infinity, or does not exist. And the only way you can tell is you're going to have to go back to the basics of limits. All right, here's an example right here. I want you to take the limit as x approaches 0 of 1 over x. Okay, I try to give you the easiest problem I can give you. When you first plug in a number, what you going to get? 1, well, you're going to get 1 over 0, which officially does not exist. But is the answer does not exist, is the answer infinity, or is the answer negative infinity? Well, let me show you. So to be able to do, remember, a limit, you got to do this. You got to go back to the definition of limit. For a full limit to exist, this is called a full limit, you're going to have to take the limit as x approaches 0 from below of 1 over x, and you're going to have to take the limit as x approaches 0 from above of 1 over x. So you're going to do what we call the t-bar. Just to save some space, I put the t-bar out here. So these are going to be your x numbers. This is going to be the y coordinate. Here's your x numbers. These are the y coordinates. Okay? So, what number are you approaching? 0. From what side of 0 are you approaching? From below, right? What kind of numbers are below 0? Negative. But you want to get close to 0. So don't try -5 and work your way in. Go ahead and get close. I think in like -0.1. That's close to 0 on the left side. And then I'm going to go -0.01. Then I'm going to go -0.001. I'm going to get close, even closer, and even closer. Usually you plug in about 2 or 3 good numbers, you can catch a pattern on it. Okay? Now, here we go. Plug it in, and I'm going to use my calculator here. Plug it in. What is 1 divided by -0.1? 1 divided by -0.1 is -10. Does that make sense? I'm doing the incremental approach. I'm going back to the basic definition of what a limit is. You can always figure out a limit by just basically setting up a t-bar and just getting really, really close to the number and see what you're approaching. So let's see here. Next one's going to be 1 divided by -0.01. What do you get here? Caught a pattern yet? -100. Now, the next one's gonna be, well, we'll show it to you, 1 divided by negative 0.001, which would be negative 1,000. So, from this problem, when I take the limit as x approaches 0 from below of 1 over x, what number are you going towards? Outstanding. You're not going to a particular number. They're not getting closer and closer and closer to like 5, 4.9, 4.999, 4.99999. You know, that's approaching 5. This one's going negative 100, negative 10, negative 100, negative 1,000. This thing's going to what? Negative infinity. It's getting bigger and bigger negatively. Does that make sense? Which by definition means it's getting smaller and smaller and smaller. Does that make sense? But that's a one-sided limit. Now do the other side. Now I'll take the limit as x approaches 0 from the plus side. So I'm going to 0 on the plus side. On the plus side, I'm going to plug in positive 0.1, positive 0.01, and positive 0.001. That is approaching 0 on the plus side. So I can figure out what is the limit as x approaches 0 on the plus side of 1 over x. So when I plug in 0.1, well, I'll do it on the calculator if you really want me to. 1 divided by 0.1 is 10. I don't think I need a calculator for the rest of them. What's 1 divided by 0.01? 100. And 1 divided by 0.001? 1,000. So, as you take the limit as x approaches 0 on the plus side of this guy, what are we getting? Positive infinity. Or infinity, as you say. But here comes my question. Very important question. What is the limit as x approaches 0 of 1 over x? No. I want to remind you, and I'm going to put it in code for you guys. So when I tell you this, when you guys are walking around, and I'm saying you think about limits, and I tell you this is your definition of limit. For a full limit to exist, the limit from below has got to go to the same thing as the limit from above. You've got to approach the same number from below and from above. From below, what's this thing going towards? Negative infinity. That sucker's shooting down. And from above, what's the limit as x approaches 0 on the plus side from above of 1 over x? What's that going towards? Are they going to the same thing? So by definition, since they're not going to the same thing, what's my full limit going to be? This is a real does not exist example. Does that make sense? Compare that problem to, and I get to insert a new problem with you guys, this one. What is the limit as x approaches 0 of 1 over x squared? Slightly different, but I want you to see the comparisons between the two. All right. First rule of limits is to do what? Plug it in. When I plug in 0, 1 over 0 squared, 0 squared is 0. This is 1 divided by 0. It's one of these cases here. Does that make sense? When you have a number divided by 0, you want to do what we call the T-bar. And so now since I have plenty of room here, I'm going to draw my little T-bars like this, because that's the way I used to draw my T-bars. I'm going to draw 2 of them. Why 2 of them? One of them is going to represent the limit as x approaches 0 from the minus side of 1 over x squared, and the other one's going to represent the limit as x approaches 0 on the plus side of 1 over x squared. You're going to do your, quote, one-sided limits. This, by definition, are called one-sided limits. Now, same. I want to approach 0 from below 0. From below 0, the negative numbers. So I'm going to go negative 0.1, negative 0.01, and negative 0.001. Does that make sense? And this one, I'm going to take the limit as x approaches 0 on the plus side. So I'm going to plug in 0.1, 0.01, 0.001. Now, I'm going to use my calculator again. But this time, don't forget, we're squaring the bottom. So this is 1 divided by parentheses negative 0.1, close parentheses squared. Notice how I put parentheses around my function I'm plugging in. Very important. Without parentheses, your calculator will screw this up. What do I get? I get 100. Now what's 1 divided by parentheses negative 0.01 quantity squared? What do you get there? 10,000. And 1 divided by parentheses negative 0.001 squared. What do you get there? 1 million. So as this approaches 0 from below, what's my function approaching? 100, 10,000, 1 million. What is that? Infinity. Therefore, the limit as x approaches 0 from below of 1 over x squared is infinity. Now, do the same thing over here with the limit as x approaches 0 from the plus side of 1 over x squared. So now I'm going to plug in numbers like positive 0.1, positive 0.01, and positive 0.001. So when I do that, notice the wonderful use of parentheses here. 1 divided by parentheses, 0.1 squared, I get 100. 1 divided by parentheses, 0.01 squared, I get 10,000. And what do you think the last one's going to be? Yep, you know it, but I just want to show you. Yep, it is 1 million. Does that make sense? So now, as the x approaches 0.1, 0.01, 0.010 on the plus side, my functional value is approaching what? Positive infinity again. So now I have the limit as x approaches 0 on the plus side of 1 over x squared equals infinity. 3 dots in a triangular fashion means therefore. Mathematical symbols here. Therefore, the limit as x approaches 0 of 1 over x squared. This is a full limit because you don't see a plus minus on it. So what would the answer for this guy be? Infinity. Why is this answer infinity? Because the limit from below is going to infinity, limit from above is going to infinity. They're at least going to the same thing. Does that make sense? When they go to the same thing, that's your answer, including infinities. When you approach it, one's going to negative infinity, one's going to positive infinity, that's a does not exist case. So this is a limit where the answer would be infinity. Does that make sense? So when you have this number divided by 0 stuff, basically you got to set up your charts. Okay? So look at this next example right here. Try to throw a trig one at you guys. All right. I want you to take the limit as x approaches 0 of the sine of x over x. Okay? Now, we're now getting into throwing weirder stuff at you guys. Now, first rule of limits is to do what? Plug it in. Come on. So I'm going to plug in 0. This will be the limit as x approaches 0 of the sine of x over x. That would be the sine of 0 over 0. What is the sine of 0? Oh, I hear two answers there. We better double check it. What mode should your brain as well as your calculator be in for this class? Wrong. We're in math class. What mode should your brain be in as well as your calculator? Radians. Go to math. Excuse me, go to mode. Go to mode, and be in radian mode. In math class, you're always in radian mode. In your physics and your engineering classes, be in degree mode, because in degree mode, that will actually help you calculate particular, most folks understand degrees. But here's the deal. What's the difference between degrees and radians? Okay, well, it's pi. It's based upon the circle. If you go all the way around a unit circle, how far do you go all the way around? You go in increments of pi. So all the way around a circle is doing 2 pi. Okay, so and it's based upon the circumference formula. You remember the circumference formula for a circle? 2 pi r. 2 pi times the radius. It's that 2 pi part that's in radians. That's where it comes from. What is pi? 3.1415926. It's a never-ending, never-repeating decimal. It is irrational. It is a God-given number. The fact of the matter is that our ancients, actually it was the Greeks that discovered this so many years ago, about 3,000 years ago, that every time that they took a circle and divided by the diameter. This number, whether it was a big circle or small circle, this number 3.141599269 popped up. They used to use the fraction 22/7 because they didn't round it to too many decimal places, and that gave them enough accuracy to be happy because they were making wheels on wagons and putting rims of metal around them to make the wheel last longer and stuff like that, but they didn't know how much metal to use and stuff. So they were using some very advanced mathematics, but they discovered that every time that whether it's a big circle or small circle, this number just shows up. It's a literally God-given number. Key to mathematics. Galileo once said, mathematics is the alphabet for which God wrote the universe. This is why we study math. And the other reason why you cannot do all these other sciences without knowing math first. You can't be an engineer without knowing the mathematics behind it first. Or a chemistry, biology major, physics major, they all boil down at some point to the mathematics behind it, okay? But circles are based upon that pi number, 3.141599269. Where did degrees come from? Degrees came from basically the Sumerian culture, which was 3000 BC. The Sumerian culture, which was between the Tigris and Euphrates River. Some of you guys may know it better as Baghdad area, and that would be correct. It was from that Baghdad area that we, a few years ago, just bombed the hell out of. But here's the thing. This is the Sumerian culture. They had a numbering system. Our numbering system is the Arabic numbering system. We count 1 through 10, and then we start over again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then what do we got? 11, 10, and 1. 12, 10, and 2. They have, and that's called a base 10 numbering system. They had a base 60 numbering system in the Sumerian culture. They would count 1, 2, 3, 4, 5, 6, 7, 8, 9, 59, 60, and then they start over again. 61 was 60 and 1. 62 was 60 and 2, and that's how their symbols went off. From a math perspective, that was not the greatest numbering system in the world, but these guys were very good at worshiping the stars, and they were very good at analyzing geometric shapes throughout the heavens. So when they did 660s, when they were measuring through the atmosphere, 660s, they went all the way around a circle. What is 660s? 360. And every time they moved, it was a degree. That's what they called it. So 660s is 360. You done a donut. You went 360 degrees. You went all the way around. Now, there's culture, even for today, we use it stuff. That base 60 numbering system. For example, how many seconds in a minute? 60. How many minutes in an hour? 60. How many hours in a day? That's so sad. How many? It's not the greatest numbering system in the world. So, but that first part we still use today. And even when we measure angles, we like degrees. And it's actually from their numbering system years ago. Okay? But when you're actually doing real mathematics and trying to get to the science and theory behind it, you want to be in radian mode. Use the pi stuff. It works a lot better than a Sumerian culture numbers from 3000 BC. All right? So, here's the deal. Let's take a look at this guy here. I got 2 minutes. All right, take the limit as x approaches 0 of the sine of x over x. First rule of limits is plug a number. When I take the sine of 0, what do I get? The sine of 0 is 0. So I get 0 divided by 0. Now here's the real deal. This is why this is such an important problem. 0 divided by 0, what am I supposed to do? Do algebra. What kind of algebra would you do on this thing? If I was going to do algebra, I take the limit as x approaches 0 of the sine of x over x. What kind of algebra would you do? What kind of algebra can you do? Well, here's your problem. That's a trig function, and that's a degree 1 polynomial. They're not like terms. There's no algebra to be done. Now, how many of my students do this? You'll be amazed. And what are you left with if the x's cancel? No, you're left with sin. Sin. And that's exactly what you committed if you did this. That's embarrassing. You can never cancel an angle on a trig function. It's part of its function. That will never cancel. So here's my point. So if you ever do this, you have committed this and go straight to you know where. All right, so don't do this. Here's the deal. There is no algebra. I can't do any algebra. So on this kind of problem, when there is no algebra done, you don't have to do a choice. You're going to have to do the t-bar. Okay? It's not just with numbers divided by 0 type of an example. It's also when the algebra can't be done. Does that make sense? And there are some problems out there that the algebra you can't do. Then nothing's going to be able to cancel because they're not like terms. So on this one, x and y, I'm going to approach 0, and I got to take the limit as x approaches 0 from below of the sine of x over x. I'm going to take the limit as x approaches 0 from above of sine of x over x. From below, I'm going to plug in numbers like -0.1 and -0.01 and -0.001. And from above, I'm going to plug in 0.1, 0.01, and 0.001. So here we go. The sine of -0.1 in radian mode, very important, divided by -0.1. What do I get? 0.9983. 4 decimal places is good enough. Now, plug in the sine of -0.01 divided by -0.01. And notice I'm using the recall button to do it faster. What do I get? 0.99983, whatever. Now I'm going to plug in sine of -0.001 divided by -0.001. The right order there. And what do I get? 0.9999983. As this thing approaches 0 from below, what's my numbers approaching? They're approaching 1. Does that make sense? Now if I plug in +1, the sine, it's positive 0.1, the sine of 0.1 divided by 0.1 is 0.9983. The sine of 0.01 divided by 0.01 is 0.99983. And so you notice I'm getting the same numbers again, whether it's negative or positive. I get 0.999999983, which again is approaching 1. So as my limit from the left approaches 1 and the limit from the right approaches 1, what will the full limit approach? 1, because the limit from the left is equal to the limit from the right. Now officially what's going on here on this particular graph, and we'll look at the graph next time, so bring your calculators. We're going to graph this thing. You're going to see actually there's a hole in the graph. And you just discovered where the hole is located at. When x is 0, the hole's going to be at 1. We'll study more of this stuff next time. See you guys then. Sure.